Okay, so we're going to sum up all the heat input that is being inputted to the system. So that will be for the compressor. So we have 698, that we point 6165. So the units is kilojoule per minute. Then for our evaporator, so this will be 2197. So this is 0.12. The units will be kilojoule per minute also. Then I'm gonna add for the so we have already evaporator, compressor. For the pipeline, from evaporator to compressor, so we have, I'm gonna add also 50.225. So we have the units of kilojoule per minute, then plus the heat or the heat input from condenser to expansion valve. So that will be 19.46. So that will be kilojoule per minute. So finally we have the total heat input, which is equal to, so we have 2000, that will be 965.42. So kilojoule per minute for the total heat input. So next, let's go to the heat rejected by the system. So we'll be starting with the jacket cooling water. Now for the jacket cooling water, so let's review our solution previously. So we have 186.3215. Then next we go to find the heat rejected in the pipeline from compressor to condenser. So we have here your compressor and going to your condenser. So we have this one pipeline, so from 2 to 3. So we have the heat from 2 to 3, so that will be the mass flow rate of your ammonia multiplied by the change enthalpy from 2 to 3. So for the value of enthalpy 2, so looking back from our data gathered, so we have 1725. So our mass flow rate of ammonia, we have 2.009, that will be kilogram per minute. Then we shall multiply it by the 1725. So minus the enthalpy at 0.3. So 0.3 we have 1700. So we have 1700. So this is kilojoule per kilogram. So cancel out your common units here. So cancel this one and this one. Okay. So we have the value of your heat from pipeline from 2 to 3, or heat being rejected at that point, is equal to, so we have, that is 50.225. So this is kilojoule per minute for our units. So next, let's go to the condensing cooling water. So condensing cooling water is the heat that is being rejected by our condenser. So that is the circulated water that will going to extract the heat from the condenser from 3 to 4. So again, we have your equations here. So for condensing water that is required to cool our condenser, so we have the mass. Again, we'll be using again mass of your ammonia multiplied by the change in enthalpy from 0.3 to 4. So we have the value. So from our table, your enthalpy at 3, so we have 1700. So this is multiply first our flow rate of our ammonia. So that will be kilogram per minute. So we have enthalpy 3, that is 1,700. Then, and for our enthalpy 4, looking backward table, for enthalpy 4, okay, for enthalpy 4, we have 341.76. So we have 341.76. So we have the units of here, kilojoule per kilogram. So let's cancel the common units here, this one and this one. So we have now the value of your water required to cool our condenser, which is equal to, so we have the 2,728. Okay, so this is kilojoule per minute. Now for our total heat rejected, so that will be the jacket cooling water, which is 186.315. So that is kilojoule per minute. Then we shall be adding your pipeline from compressor to condenser, so that will be 50.225 kilojoule per minute. Okay, then plus our condensing to cool our water to cool our condensing unit. So we have 2,728 kilojoule per minute. So summing up that all, we have the value of, so that is 2,964. So this is 0.54. So we have the units of kilojoule per minute. Okay, so that summarizes our solutions here. So we are able to already solve the last questions here. So last unknown here. So I'm gonna check this one. Okay, so looking at the overview of our solution, so starting from our initials. Okay, so looking at the overview, and this one, part 2. So okay,